Welcome back. In this section, we'll be talking about polynomial functions, properties of them, and also graphing polynomial functions. A couple of things to mention here. For a polynomial function of degree n, remember that degree n means that x to the power of n, that's the highest power of x that we have in our function. Remember that for polynomials, the powers of x can only be positive whole number powers only. So for all of these x's that we have, these are all whole number powers. There are no negative powers. There are no fractional powers. For the coefficients, though, those can be any number we'd like. So an minus 1, all the way down to a2, a1, and a0. Those can be any real number we'd like. The only restriction that we have here is that the coefficient an, the leading coefficient, can't be 0. And that's, of course, if we want to have the highest power of this polynomial being a power of n, then that means that we have to have that x to the n term. That's why an couldn't be 0. We have names for the special terms. The one with the highest power of x, we call that the leading term. Leading term does not necessarily mean that it's the first term that we've written out, so be careful about that. Even if I wrote the terms in a random order or changed the order so that the highest power appeared later, that still would be the same leading term for that polynomial function. The constant term, that's the term that has no power of x. Of course, every polynomial has a constant term. That term could be 0. So if you see a polynomial function like, for example, f of x is x to the power of 5, that is a polynomial, and it would be a polynomial function whose constant term would be 0. We've already seen linear functions. Those are polynomial functions with degree 1. Quadratic functions, those have degree 2. A constant function is a kind of a polynomial. So something like this, the constant function f of x equals 3, that is still a polynomial. You would call it a polynomial with degree 0. The highest power of x is 0 because there are no x's. That the constant term 3 could be thought of as 3 times x to the power of 0. So again, for the powers of x, they can only be integer powers that are not negative. So if we see a negative power or if we see a fractional power, then that means what we've got is not a polynomial. So something like f of x being square root of x, not a polynomial. G of x being 1 over x, also not a polynomial because that would then be x to a negative power. And it would also be true for anything where any of the terms happen to have negative powers or fractional powers. So if you had a function that had x to the 5, x to the 4, 3x cubed, and then I have a square root of x, because of that term, this is no longer a polynomial function. So when we're writing out our functions, typically what I'll write them out in is standard form, going from the highest power to the lowest. You're not really required to do that. It is a good idea. It helps you keep from losing terms by accident. It's very easy if you've got a big polynomial to drop a term somewhere along the way, and if you have your terms written from highest power to lowest, it's easier to keep track of things. So for this polynomial that I have, f of x, it's not written in standard form, and so I might want to do that first. I might want to first start off with rewriting f of x as 10x to the 7 minus 6x cubed minus x squared plus x plus 4. There we go. So again, the degree for this polynomial, that would be the highest power of x. And so in this case, the highest power of x is 7. So that would be degree 7 for this polynomial. The leading term would be that x to the power of 7 term. So you could also say that the leading coefficient is 10 for this polynomial. And then finally, the constant term that we have is positive 4. One of the nice properties of polynomial functions is that their graphs are all kind of similar in a sense. Every polynomial function has a graph that is smooth, no sharp corners like we might have in the absolute value function, where it's a sharp corner that happens there at x is equal to 0. We never see anything like that with a polynomial, just nice smooth curves that go up and then down and then up and down. The other thing that's true about polynomials is that they are continuous. In other words, there are no breaks, there are no holes, no skips, and no jumps. That also means that for a polynomial, they are defined for all real numbers. The domain is always from far left to far right. One other nice property is that for polynomial functions, the y-intercept, the coordinate for the y-intercept, is always the constant term. And the reason for that, of course, is if you're looking for the y-intercept for your function, you would be letting the x value be equal to 0. But if we let x be equal to 0, then all of these terms that have x's in them would all be equal to 0, leaving only the constant term. So that's the reason why, if we were interested in finding the constant term for a polynomial, that would be the same thing as finding the y-intercept for our polynomial. So that's one of the nice features for any polynomial. If it's written in standard form, we can easily identify the y-intercept. All right, we're going to now talk about power functions, which are a special kind of polynomial function, one in which we have any real number constant, just as long as it's not 0, multiplied by x to some integer power. Now, I'm specifying here that n has to be greater than 0 in order for this to be a power function. Other books will say different things. So for us, we're looking more at things like 7x to the 5, or maybe something like negative 12 times x to the 6. But you will see other books that would call something like 10x to the negative 3. They would also consider that to be a power function. But as I said, for us, we're mostly going to be interested in power functions where the power is a positive integer. We're also going to see that later on, when we talk about the graphs of polynomial functions, that the end behavior, what happens at the far left and at the far right of our graph, has something to do with the graphs of power functions. Now, we're interested in particular in power functions where the power is positive. And so there's two cases. There's the case where the power is an even positive number, and for those, all of those are functions that happen to look like y equals x squared. They all have the same sort of shape as a parabola. And all of these would all be even functions. So if somebody were to graph y equals x to the power of 100, let's say, it would look very similar to y equals x squared. They would all be even functions, and they all pass through those 3 points, negative 1, 1, 0, 0, and 1, 1. If the power is odd, then there's two choices. Either the power could be 1, in which case you're really talking about the straight line f of x is equal to x to the 1, or y equals x. That's a straight line with a slope of 1 and a y-intercept of 0, 0. But for all the other odd powers, 3, 5, 7, and so on, all of those functions have a graph that looks pretty much the same thing as y equals x cubed. And those are all odd functions, and they all pass through the three same points, negative 1, negative 1, 0, 0, and 1, 1. So we'll do a little bit of graphing here. I'm going to graph this function negative 4x plus 2 to the 7 using transformations. And so the basic shape that we're working with is y equals x to the power of 7, which we know that x to the power of 7 looks shockingly similar to x cubed as far as the graph goes. So if you were to say, what's the graph of y equals x to the 7, I would say it looks a little something like this. It would pass through the points 1, 1, 0, 0, and negative 1, negative 1. And then for the rest of my graphing, I'm going to be doing it via transformations. And so notice I've got two transformations going on here, one of these being a horizontal shift to the left by 2 units, and then I've also got a vertical stretch and a flip. So I'll start with the horizontal shift to the left by 2. So this is subtracting 2 from every x value. So the point -1, -1 has moved to -3, -1. 0, 0 is now at the point -2, 0. And 1, 1 has moved 2 to the left to -1, 1. And there we go. This is my graph of y equals x plus 2 to the power of 7. Just going to make this look a little bit smoother. There we go. All right. So the last thing that I need to do is my vertical stretch and flip. And remember that I would be doing that by multiplying all of my y coordinates, in this case by -4. So the first point that I had, which was -3, -1, I'll multiply that y coordinate by -4 to give me the point -3, 4. The next point, -2, 0, stays there. The y coordinate when I multiply it by -4 stays as 0. And the last point, which was -1, 1, when I multiply its y coordinate by -4, I get the point -1, -4. And of course, last thing for me to do is just to label my points. The only one that I don't need to label is the one that's at my tick mark on the x-axis. And there was our function f of x is -4 x plus 2 to the 7. We'll do one more. Here I've got g of x being a transformed x to the power of 6 function. And for x to the power of 6, that should look pretty much the same thing as a parabola, y equals x squared. So same 3 points, same general shape. And as far as my transformations go, I have one transformation that's a vertical stretch. We're multiplying all of our y values by 2. And then we'll do a vertical shift downward by 1. So first we'll multiply all of our y values by 2. So we have our point 1, 2, 0, 0 stays where it is. We have the other point -1, 2. This is y equals 2x to the 6. And then as my last move, I'm going to then take this graph and shift it downward by 1 unit, and that will be the graph of g of x. So all of my points, shifting them downward by 1 unit. And that is my graph of g of x. 2x to the 6 minus 1.